Now, typically out of these three steps we just discussed, the most difficult one is the last one, finding the parameters that make the derivative equal to 0. Now, in this example, it was straightforward, but as you will see, as we get bigger and bigger models and hypotheses, that we're going to probably have to find an approximate iterative process to give us an estimate for the values of theta. It's going to be a vector, obviously, of parameters that minimizes the log likelihood function. So this example also gives us another warning here, which is when the data set is small enough, some events may not have been observed. So, for example, say, for example, we opened 5 candies and all of them came lime. Now, it's not realistic. According to this model, we will say that theta is 0 because C is 0, right? We haven't opened any cherry candies. Now, that's probably not realistic and incorrect. It's just that we didn't collect enough data to make an accurate prediction yet. So, when the data is small enough and some events have not yet been observed, the maximum likelihood hypothesis will assign 0 probability to these events. And we're going to have to find some tricks depending on the model we're trying to optimize to deal with this situation. Now, let's look at another example. Let's say we have a new candy manufacturer that gives us a little hint as to what's inside the candy based on the color of the wrapper. Okay. For example, let's say we have red and green wrappers. So the wrapper for each candy is selected probabilistically. So we can't, I mean, if we knew already that every cherry candy is in red and every lime is in green, then we wouldn't need machine learning, right? We would already know the proportion of cherry in the bag. But what we're told is that the wrapper for each candy is selected probabilistically according to some unknown conditional distribution depending on the flavor. So it's not deterministic. It's not every cherry candy will have a red wrapper. It's probabilistic based on some unknown distributions that we don't know. Now, in that case, the model will have to change. The Bayesian network will have to change. So we will have, we can observe the wrapper. Okay. We will have 3 parameters now. So we'll have theta, which is our original parameter. And then we will have theta 1 and theta 2, which are for the probability of the wrapper being red given cherry, it's theta 1, and the probability of the wrapper being a red wrapper given that it's a lime candy is theta 2. Okay, so in that case then, the probability that the flavor is cherry and the wrapper is green, okay, given a given value for theta 1, theta 2, will be this equation right there. So it will be theta times 1 minus theta 1. So this is the likelihood of a cherry candy in green wrapper. Now, if I have n candies and RC of them are red wrapped cherry candies, then this would be my likelihood function. So that's the probability of observing this data, which is RC, red wrapped cherry candies, and then GC, which is green wrapped cherry candies, and of course L is our lime candy. So we take the log of this once again to help us take the derivative, and now we have three parameters, so we have to take three partial derivatives. Going to be partial L partial theta, partial L partial theta 1, and partial L partial theta 2. Okay, so we take the three derivatives, and here also we can still solve the problem exactly using algebra. We don't need to use any numerical approximation. We find that theta is C over C plus L, and theta 1 is red wrapped cherries over the total number of cherries observed, and theta 2 is red wrapped lime candies over the total number of lime candies we observed. Okay, so theta 1 then, remember that's the probability that a cherry candy has a red wrapper, and same for theta 2, the probability that a red candy has a lime wrapper. A lime candy has a red wrapper. So you can see that these results can be extended then to any Bayesian network whose conditional probabilities are represented in a table like this one. Okay, so once we have the conditional probability like this, then we can definitely do our Bayesian network and follow this process. The most important point to notice here is that for a Bayesian network with complete data, the maximum likelihood parameter learning problem breaks down into separate learning problem, okay, one for each parameter. As you can see, the derivative with respect to theta has no theta 1 in it or theta 2, and same for theta 1, it's only a function of theta 1, and same for theta 2. Okay, so they're independent problems essentially that you can deal with each of them separately. Okay. The second point is that the parameter values for a variable given its parents are just the observed frequency of the variable for each setting of the parent. So to get theta 1 here, all you need to do is, okay, how many total cherries did we have? And how many of them were wrapped in red? That's it, essentially. So it's a fraction of red cherry candies out of all the cherry candies we did. So very easy to just look at the parent in the Bayesian network and estimate the probability. So, of course, as before, we have to worry about zeros in the denominator, or if we haven't seen any red wrapped lime candies, for example, in our sample, and so on. So we just have to pay attention to that. Now, this essentially is the foundation to what we call naive Bayes models, okay, which are probably the most common Bayesian network model used in machine learning. So in this model, the class variable C, which is to be predicted, is the root, and the attribute variable xi are the leaves. Okay, so the model is naive because it assumes that the attributes are conditionally independent of each other given the class. Okay, so in this case, in our previous example, we only had one attribute for each candy, which is the color of the wrapper. But we could have other attributes, like, for example, the weight of the candy, if there was a difference between cherry and lime, for example. So we could have other attributes for each parent. Now, this approach assumes that the distribution of each attribute is independent of the other. So which in this example would mean that regardless of the weight of the candy, the distribution of the wrapper color, whether it's red or green, has nothing to do with the distribution of the weight. Okay, so that's why we call it naive, because it just assumes that each distribution is independent. So in the case then maximum likelihood parameter values then are found in this method the same way. Okay, the probability for each class. Okay, so the probability of cherry, for example, or class C, will given the values of the attributes, so the color of the wrapper, the weight of the candy, and so on, is just the product of the probabilities obtained from each attribute. So a deterministic prediction can be obtained by choosing the most likely class, as we've done before. So this method learns fairly quickly, but not as quickly as decision trees learning. And the explanation is that the true hypothesis, which is a decision tree, is not representable exactly using a naive Bayes mode. So naive Bayes learning turns out to be surprisingly well in a wide range of applications. Okay, and it scales well to large problems with n Boolean attributes. Okay, so actually you can see here a comparison between the performance of a naive Bayes model in dotted line and decision tree model in solid. Okay, you can see the learning curve as the training size increases. It's not too bad given how simple the model is. Okay, so this gives a good introduction. We can then build on to more advanced machine learning models. Just if you want to take something out of this lecture, just remember the process we discussed. We write a likelihood function, take the log, and then find the derivative with respect to the parameter, and find the set values of parameters that maximize the likelihood function, and that will be the parameters of our learning models. Now, these parameters later on will be weights in neurons, and will be also decision points in decision trees and so on, but the process remains the same. Okay, see you in class.